Hello, welcome back to the lecture for this week's material. We're going to continue with chapter 3. This is section 3.3. And in the past, we had talked about measures of center, what the center of the data was, measure of spread, kind of give us an idea of how spread out the data was or how tight it was. And this is going to be measure of position. So if I had an individual point of the data, how does it look in reference to every other points, or where does it sit in from left to right? So this is measures of position. So let's get started. So the first thing we're going to need to talk about is a z-score. Z-scores are used in many different situations. One in particular that we look at is if we need to compare two individual pieces of data where the data isn't really from the same data set. For example, if who is taller? So if I've got a man 73 inches tall or a woman 68 inches tall, well, we know absolutely that the man is taller, the 73. But what about if we're asking a different question? We're asking the question, who is taller in relationship to their sex? So is the man tall or short compared to other men? Is the woman tall or short compared to other women? And one way that we can answer that is by looking at the men's average, the women's average, and then computing this thing called a z-score. And in doing the z-score, we're going to need both the mean and the standard deviation for both the data sets in order to calculate that individual z-score, and then we're just going to look at the z-scores comparatively. So suppose the question is asked this way: who is taller relative to their gender, a man 73 inches tall or a woman 68 inches tall? One way to answer this question is with a z-score. So the z-score of an individual data value tells how many standard deviations that value is from its population mean. So consider that if I give you two different measurements of a wall length, one is in inches, one is in feet. If I say 72 inches, and if I say 6 feet, that's two different ways of that same measurement. The z-score gives you just a different means of measurement, and it's in terms of standard deviations of that particular data set. Okay. For example, a value one standard deviation above the mean has a z-score of z equal 1. So once we convert, it's going to be into a standard measure, and we can look at the standard measure and say, okay, if I've got a +1, it is one standard deviation, whatever that standard deviation is for that data set, above the mean. If I've got a value of 2 standard deviations below the mean, then I have a z-score of -2. That's 2 standard deviations, whatever the standard deviation is for that data set. Okay, so I can't compare directly to z-scores, but I can compare them to their mean, and that's what I want to do with that question. So let x be a value from a population with a mean mu and standard deviation sigma. The z-score for x is z. So what I'm going to do is subtract off the mean of that data set. So if x is bigger than the mean, that's going to be a positive number. And if x is less than the mean, that's going to be a negative number. And if x is exactly equal to the mean, this thing's going to be 0, so the z-score is going to be 0. Okay, but we're going to take it, we're going to subtract off the mean, and then divide that distance in terms of the standard deviation for that data set. So here's an example. A National Center for Health Statistics study states that the mean height for adult men in the U.S. is mu equals 69.4 inches with a standard deviation of sigma 3.1 inches. The mean height for adult women is mu 63.8 inches with a standard deviation of sigma 2.8 inches. Who is taller relative to their gender, a man 73 inches tall or a woman 68 inches tall? So what we're going to do is compute each individual z-score in relationship to their mean and standard deviation. So for the man's height, the mean was the 69.4. That's the measure of that particular person, that particular man. We calculate this, divide it by their standard deviation of 3.1, we get a z-score of 1.16. The women's height, 68 minus 63.8, divided by that standard deviation of 2.8, gives you 1.50. It's a pure number. And basically what this tells you is that this is further away from the mean. The closer it is to 0, that's kind of the average, so they would be an average. This one is closer to the average height of a man than the woman, so that gives you an idea of who is taller or relative to their sex. So the woman is, let's read this out, hold on. The woman is taller relative to the population of women's heights. Since the z-score is the number of standard deviations from the mean, we can easily interpret the z-score for the bell-shaped populations using the empirical rule. When a population has a histogram that is approximately bell-shaped, then approximately 68% of the data will have z-scores between -1 and 1. So we compute their z-scores. We've got the mean. The mean would be a z-score of 0. And if we recognize that the data, the histogram of the data, shows us that it's a bell-shaped curve, then the data between 1 and -1, 68% of the data, or the values of those are between plus and minus 1 of the mean, okay, the mean being 0. Approximately 95% of the data will have z-scores between -2 and 2. So this includes that 68% and then a little bit more on the outside. That's between z is equal to 2 and z is equal to -2. Almost all of the data will have z-scores between -3 and 3, and that's usually computed like at 99.7%, I think is what you'll see. So we've got the mean, the median. Again, how can we look at data, display it, I can take a data set and kind of put it in relationship to everything. This is another way we can do is in quartiles. And quartiles basically divides a data set into 4 approximately equal pieces. So it's not the individual data points, but if I just started counting, I got the first one, second one, third one, fourth one, all to 20. And if I divided each one into 4, which give me 5, and then 5 and 5 and 5, each one of those 5 data points give me a quarter of the data. The quartile gives me what is that number corresponding to that 5th position, and everything less than that is in the first quartile. Between the 1 and the 2 is the second quartile, and so forth. So every data set has 3 quartiles: first, second, third. The 4th is the max. The 0, it would basically be the bottom, the minimum number. We're going to talk about the 5-number summary in just a minute. The first quartile, denoted Q1, separates the lowest 25% of the data from the highest 75%. The second quartile, denoted Q2, separates the lowest 50 from the highest 50. And then Q3 separates the lowest 75% from the highest 25%. All of these should add up to be 100% when we're talking in those terms. So how do we compute these quartiles? This is one procedure. I mean, there's many ways, and you may not get, if you do Excel, if you do the calculator, you might not get exactly the same number that what you would calculate it, but this is a reasonably easy way to go about calculating quartiles. So what you're going to do is arrange the data in increasing order. Just like we would find the median, we're going to sort the data. And then I've got the n number of values, and I'm going to do first quartile. Basically, I'm going to compute the position. So I've got, if I had the 20 times my 1/4, that would be the 5th position. If I do the third quartile, that's the 75% of the number. That would be the 15 of 20, so 0.75 times the 20 should give us the 15. So we do this, we compute the location. That's what the L is for, is the location of it. So I get this number, the 5, the 15. If it's a whole number, the quartile is the average of the number in position L and the number in the position L plus 1. So between the 5th and the 6th, I'm going to average those out, and that's going to kind of give me what everything would be less than that number. That would include that number that's in there. Okay. If it's not a whole number, I'm going to round it up to the next higher whole number. The quartile is the number of the position corresponding to the rounded up value. If we did this, something that we already know how to do is the median. If I did this with the median, that would basically say the median, if I did 20 data points, 0.50 times the 20, well, half of the 20 would be the 10. If I've got an even number, you remember how we handle even numbers, I'm going to average the number between the 10th and the 11th position. That's what this is doing. If I come up with, if I had 21 data and if I did the 50%, the half, I would come up with 10.5. So I would round it up that next position, that would be the odd one, the 11th position. I'd have 10 below, 10 above that 11th position, and this would give me the odd number is basically what this would be doing. So here's, let's go through this. The following table presents the annual rainfall in inches in Los Angeles during the month of February over several years. Compute the quartiles for the data. Okay. So we've got it all, let's see, it looks like it's all already sorted for us. They're n equal 45 values. For the first quartile, we compute the location, 0.25, so that's the quarter, the first quartile, times the 45, that gives us 11.25. Since I have a decimal number here, I'm going to round that up, according to that rule, up to 12. And the first quartile is the number in the 12th position. Okay, so we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that one would be the position that we would go for. So the number, the first quartile is 0.92. So the number, 25% of the data is less than 92. Those are the 25% that's less than that. For the second quartile, that's basically the median. So either way that we would want to do the Q2, it should be the same thing. I'm going to have the 45, the 50% of the half would be the 22.5. That would be the 22, and then the 23rd position. And if we go back, that's the 3.12 if I count it up. That's the odd position out. Half the data is below, half the data is above. And finally, for our 75th percentile, these are later going to be called percentiles as well, but the third quartile is 75.75 times the 45. That gives me 33.75. Again, I need to round up to 34 to get that one. And the 34th would be the 4.94. If I went through and counted them up, that is the 34th position. 34th, 5th, 6th, 7th, 8th, 9th, 10th, 12th, 13th, 14th, 15th. That's the 45th. 15 above. Okay. So here is the quartiles. If you have a 84 plus, kind of a quick review, the 1var stats, commands in the TI 84 plus. So if I go into stat, press the stats, go to the calculate 1var. Once you enter these into your L1 table, so edit, enter them into your L1, then calculate from the 1var stats. It'll give you this kind of readout, the mean, the X bar. This mean could be either the sample mean X bar or well as the mu, the population mean. You have to determine which symbol you're going to use. If you have entered sample data, you will use X bar. If you have entered population data, all of the data that you know, or all the data that's out there that you're concerned with, you would write mu is equal to, but that number corresponding is going to be the very same thing. Now, the standard deviation numbers for a data set depends on if it's a sample or a population. So it gives you these two numbers. And again, you have to say, oh, if I'm a sample, I'm going to use S of X. And if it's a population standard deviation, if I've got all the data that I'm concerned with, I'm going to use sigma X. Min X, that's the minimum data value. The first quartile is Q1, the median is the Q2. Q3, the third quartile, and then the max data value. That's what the 1VAR returns, whether you're using the TI-84, the 36, or the 30. Will give you these kind of results. Okay. So take a look at this, even though just be aware that you may see this type of picture and it's going to ask you different things. And be able to pull it out from a little picture like this. Here's the standard deviation if it's a sample, sigma X if it's population data. Here's my number of data members, and here is what we're going to call the 5-number summary as we go forward. So here's visualizing the quartiles. So here's the data that's in there. Now what I'm going to do is say the value that you see here as the first quartile, most of that data, or 25% of the data, is going to be in here. 25% of the data is between the first quartile and the median, then the third quartile, and then the last quartile, between third and the max, the largest data. The percentiles are going to be done pretty much the same way. Percentiles is just down to the hundredth. So those were down to the quarters, right? 0.25, 0.5, 0.75. But what if I wanted to know the 30th percentile? What's the value that 30% of the data falls under? So that's what the percentile does. The procedure is going to be the very same, except I get more granularity instead of 0.25. Okay. So quartiles describe the shape of a distribution by dividing it into fourths. Sometimes it is useful to divide a data set into a greater number of pieces to get a more detailed description of the distribution. So percentiles divide a data set into hundredths. For a number P between 1 and 99, the P percentile separates the lowest P percent of the data from the highest. So it just basically gives you a delineation between those two. The procedure, computing percentiles, is the very same thing. I'm going to have the data arranged in order. And now if I wanted, like I said, if I wanted the 30th percentile, this is 0.30. The 30% is 30 divided by 100.30, 2 decimal places to the left to give me the decimal number. And I just multiplied that times the N, and the L means the location. So I go to the location. If it is a whole number, I average the L and the L plus 1 location. And if it's not, I just bump it up and use that value in there. So this is the same procedure, except these numbers were only 0.25, 0.50, 0.75. Okay. So compute the 60th percentile for the data. The same value, the number here's the same data, got 45. But now I'm going to do 0.60, 60th percentile. 0.60 times 4/5, that's 27, a whole number. So I'm going to average between 27 and 28. So I go to the 27th and 28th, and this should be, if I'm just using this data back as a reference, but that should be the 27th position. That's the 28th position, and I'm just averaging those two, just like I do the median, but it's going to be the middle two if I have an even number. Yeah. So the average of these two is 3.64. That would be the 60th percentile. And here's how it looks if we did a plot of, here's all the numbers. These are the positions, and then that would split these things out. Oh. I'm sorry, these are not the position. These are the data between here and there. Okay, sorry. So what if we wanted to do, I have a given value, a given X, And I would want to know what is that the percentile corresponding, what percentage would be less than that. Okay, so this is computing the percentile from that number. What is that percentile? So again, they arrange the data in increasing order, and then I'm going to let x be the data value whose percentile is to be computed. I want to take that, add 0.5 to it, just kind of give me a little fudge factor in here, and then divided by the number of values in the data set. And then round the result to the nearest whole number. Okay. So let's do this. Following table presents the annual rainfall in inches in Los Angeles during the month of February over several years. 1 year, the rainfall was 1.90. What percentile does this correspond to? So I have my 1.90. They're n equal 45 values, and they said there are 17 values less than 1.92. So I've got my number of values less than x, my 17, add the little piece of it here, and then divide by the 45. So that's going to be 38.9. So the number of values less than x, I identify those. I want to know the values less than 1.90. I go here, I count back, and then that would be 17, add 0.5, divided by 45. This gives me the decimal number, multiply it times 100, and that'll give me the 38.9. Round it up, that'll be the 39th percentile. So 1.90 corresponds to the 39th percentile. So once we've done everything, the 5-number summary just considers everything that we already know. What's the minimum? What's the maximum number? The 5-number summary is the min, the Q1, Q2, Q3, the Q4, which is the max. The Q2 is the median. So this is the 5-number summary, just tells us, says here, ask you for everything that you already kind of can do, okay? So here's the 5-number summary. The minimum, the smallest, the maximum, first quartile, median, and the third quartile. So we previously computed all of this stuff. The Q1 was 0.92. The median was 3.12. The Q3 is 4.94. The minimum value over here in the table is 0. The maximum being 13.68. So the 5-number summary, the minimum, Q1, Q2, Q3, and then Q4 are the max. So all of these are given in the var stats. When you do that summary, that gives you everything you need to know. You've got the mean, the standard deviation is the n, and here's the 5-number. This little arrow says that the rest of the stuff is up here. So if you wanted to go back and get the mean, you may have to go back up and hit the arrow, or you will have to go back up, hit the arrow key, and that goes back and get those. So what about outliers? So if we take it where, again, we're looking at a particular data point, is that within the reasonable values of what we're expecting, or is this something out of the ordinary? That's the outliers, okay? An outlier is a value that is considerably larger or considerably smaller than most other values in a data set. Some outliers result from errors. For example, a misplaced decimal point may cause the number to be much larger or smaller than the other values in a data set. Some outliers may be correct and simply reflect the fact that the population contains some extreme values. If you were doing it like average temperatures, you may have hit a hot day that you just normally wouldn't see. The outlier would flag it. You would go back and check, is that data correct? Was it really that hot or that cold on that day? And it may be. Or it may be that instead of 10 degrees, somebody entered an extra 0 to give you 100 degrees. So here's the temperature in a downtown location is measured 8 consecutive days during the summer. Here are the readings in Fahrenheit: 81.2, 85.6, 89.3, 91.0, 83.2, 8.45, 79.5, 87.8. Which reading would you think is an outlier? That is kind of pretty obvious at this point. That would be an outlier, and I'm pretty sure that it wasn't 8 degrees during the summer. if all of these days are that warm, it was probably 84.5, and they just put the decimal place in the wrong place. So the outlier, 8.45, and if you go back, lock the reserve for a misplace, you should be go back and correct it if you can. If you have a long list of data, you may not say, well, this may not be, I'm not for sure if that was a decimal place. It may look really, really strange. You may just want to throw that out as just a misentered data and reduce your data set, the number and everything. So that's kind of cleaning up your data set if you need to. So which ones do you start looking for as being an outlier? Then what you want to do is go ahead and sort your data, calculate your Q3 and your Q1 position, and this interquartile range is just Q3 minus Q1. Third quartile minus the first quartile. That gives you the interquartile range. Once you get that, then you're going to go back and compute the boundary points. So here's a frequently used method. Find your first quartile, your third quartile, interquartile range, Q3 minus Q1, and then you're going to have some boundaries here. Your lower outlier boundary is Q1 minus 1.5 IQR times your IQR, Q3 plus 1.5 times your IQR. That's going to be the upper boundary. So this kind of extends Q3 up to a point, Q1 down by this factor, and anything below that is outliers. Anything above your upper boundary is considered an outlier as well. Yeah. Any data value that is less than the lower outlier boundary or greater than the upper outlier boundary is considered to be an outlier. Okay. So here's the following table presents the number of students absent in a middle school in northwestern Montana for each school day in January. Identify any outliers. So what we're going to do is order these things up, compute quartiles from the 5-number summary if we just enter them on the calculator, do the IQR, and then do the boundaries, and then look at the data. Okay. So here was the Q3 and Q1. The IQR is going to be 59 minus 45, 14. Your lower boundary is going to be 45, that Q1 minus the 1.5 times 14, 1.5 times the 14, that's 24. The upper boundary is your Q3, which is 59, plus 1.5 times the 14, that's the 80. And then we'll go back and look at any data. Is there anything less than 24? I don't see anything. Anything bigger than 80? There's 100. So that would be considered an outlier. So box plots, a box plot is very useful in displaying what the 5-number summary looks like. And also we can do an extended version of this box plot and do outliers. So a box plot is a graph that presents the 5-number summary along with some additional information about a data set. There are several different kinds of box plots. The ones we describe here are sometimes called a modified box plot. These are where normally on a regular box plot, this would be the minimum. Q1, Q2, Q3, and this little whisker right here is Q4. All the data would be in here. The modified gives you some stars. That lets you know some data is outside of those lower and upper boundaries is basically what this is. And this gets reduced to the minimum. If I didn't have any outliers here, basically it is the first. So if I had an outlier here, this would be the first number. So this value corresponding to this piece would be the first number greater than the lower boundary. This number is our biggest number that is less than our boundary. So our boundary may actually be here, and this will be the first one that's less than that. So here we go again. Let's go back and then construct the box plot that corresponds to these absence days. So we get all of our data. we get our Q1, the medium, Q2, Q3. Here's our Q2 kind of in the middle, so we can go ahead and put those down. Those are going to be fixed. 45, 51, and 59. 45, 51, 59. We plot those within the blocks, and then I'm going to draw some horizontal lines. But I want to know where our boundaries are going to be, so I computed the boundaries, the 24 and the 80. The largest data value that is less than the upper boundary is 77, so we draw a horizontal line from 59 up to 77. Even though the upper boundary is 80, I kind of stopped short there. I didn't have anything lower than the lower boundary, so I go all the way down to the minimum. The smallest data value is greater than is 41. That was our smallest, so this is our minimum. There's our maximum that's less than the upper boundary. And then we put a little X there that represent here is the outlier. So this is the minimum. So our lower boundary is somewhere here. That's our minimum, which is well above our boundary, lower boundary. Q1, Q2, Q3, and that's the largest value excluding what is greater than the outlier boundary, the upper boundary. So if you have an 84, I'm not going to kind of go through this too much. The 30, 36 is what we kind of represented the 36 I hope you've got. Represent the data in L1. Go back through second Y equal. It lets you, here's the instructions. Then one to access the plot one menu, select all in the box plot type. Okay. That's the box plot type is what they're saying. So here's the type. Go in here, select this box plot, and then zoom none to view it. There's that outline for you. Okay. So let's go back over some of that, the empirical rule. So when a data set has a bell-shaped histogram, it is often possible to use the standard deviation to provide an approximate description of the data using a rule known as the empirical rule. So again, approximately 68% of the data will be within one standard deviation of the mean. Between one standard deviation, that's within +1 and -1. That's the full range, not just the mean and 1. Approximately 95% of the data will be within two standard deviations, within two standard, plus and minus. And then almost all of the data will be within three standard deviations, 99.7 if you want to get a little finer. So when can you use this? Well, what you can do in a quick is look at a box plot and then the shape of the data to determine if you can use that empirical rule or not. Okay, so this, if we go back here, this only goes in terms of a bell-shaped histogram. So when can I use this? I'd have my data, I'd do a quick box plot, and then I'd look. Well, this thing goes further out to the right. This is kind of the corresponding data. And what you see here is that 50% of the data goes to here, but I've got some numbers way out here. So this is skewed to the right. More data is kind of going out to the right instead of being symmetric about that mean. So this wouldn't, you maybe could still use it, but it is skewed and it wouldn't be a nice set value for using the empirical rule. So here, if the median is closer to the third quartile, here's the median is closer over here, then you are looking at a lot of the data being screwed out this way. So this is kind of indicates like a little tail out here, the mouse tail skewed left. And here, if you go through, you've got, here is your median, equal distance or pretty close to being equal distance between Q1 and Q3, and then this kind of equal length data tails. That is a beautiful symmetric. A lot of the data is in here. Most of the data, you've got Q2 and Q3, that's most of your data in here. Okay. So that's symmetric. This is what you would want to use the empirical rule on. Okay. So I hope you found this informative. Go back, look at those Z-scores, how to compute the quartiles, percentiles, how to compute the percentile corresponding to a given data value, finding that five number summary, how to determine outliers for the IQR, and then construct that box plot and then be able to determine the skewness from that data. Okay, so we'll see you next time. Have a good evening.